Okay, so Ruofan, please start. And remember that from now on, every student in the presentations will prepare 3 questions for the audience. Anyone here will be randomly appointed to answer the questions. So I encourage you to pay attention. Ruofan, please start.
Today I will present the paper Variational Adversarial Active Learning published in CVF 2019. These are the author's profile. First author is an undergraduate from University of Toronto. Second author is PhD from Berkeley. The last author is a professor from Berkeley. He's also one of the co-authors who applies convolutional networks for semantic segmentation problem the first time.
Okay, please go on.
Because this work is talking about active learning, so I will briefly revisit the concepts of active learning. The success of deep learning algorithms relies on sufficient training data. However, in many cases, expert knowledge is needed to provide labels for the data, especially for those medical images. We need to hire experts who have deep understanding of the problem. Thus, data labeling is costly. That's why active learning becomes useful when we have limited labeling budget. The idea of active learning is to label a subset of data with maximum information gain. How active learning works is that first I will have small set of initial label data D0. And this data set is used to initialize the model. Then we will select subset of unlabeled data by our own definition of informativeness. After that, we send the selected data to Oracle. Oracle is human expert to label the data. Last step, we append the newly labeled data to D0 and retrain the model. We repeat step 2, 3, and 4 until labeling budget is exhausted.
Okay, so I think this process is very clear. So is there any questions for this process?
When finish the, the cycle, that means when the model think no need any new unlabeled data.
When your labeling budget is exhausted or the training performance has converged on your validation data set.
Okay, thank you. Yeah, that's a good question. Another of my good question, another may not ask a good question. Another my question is that when we retrain the model, we apply transfer the learning from the original model, or we retrain the model from the very start.
You can either fine-tune from your pre-trained model or you train from scratch.
Okay. So is there any question for the process of active learning? I think Ruofan makes a very clear explanations. The goal is that we know, because it is quite common that when we train a model, we do not have sufficient training data, right? So the model have a very good performance, maybe 99% of accuracy or 100% of accuracy. However, if we deploy the model, if we really want to deploy the models, the model is still kind of overfit for the training data. So in this case, we have no choice but to complement or amend some additional data. If we want to amend additional data, we have to label them, and label them have the cost. So we still need to, in this process, the problem setting is that how do we select the unlabeled data with the minimum labeling cost? Okay.
Sorry, may I ask? It means it needs human involved. That means the Oracle. So
yeah.
I mean, during training. Or...
yeah, but even for normal training, you have Oracle.
Oh,
you need Oracle to label your data. So it's just that now we include Oracle as one of the module in the whole active learning.
For example, actually, the Oracle here, I mean, during training, maybe it's because you are training, so maybe it's some data sets that they already have labels. They will collect labels. I mean, during training.
Yeah, but actually you need, if you do experiment, then you can, then usually you will have a large number of labeled data, and then you test how your active learning perform. But when you want to apply active learning in practical scenario, then you need a human inside the oracle.
Okay, thank you.
Okay, please.
There are some naive metrics to quantify informativeness, for example, based on top 1 confidence minus top 2 confidence, or entropy, etc. Basically, these metrics are trying to select points that are near the decision boundary, because that's where the model makes uncertain predictions. So we want to select data points there to further improve the model, and maybe like fine-tune the decision boundary further. These metrics are called uncertainty-based active learning. However, this category of active learning tend to ignore the rest of points with high confidence. But the rest of points may also be informative and may also bring improvement to model performance. Thus, another branch of research is representation-based active learning, or sometimes called diversity-based active learning. If we think about why our current model does not work well on validation set, it's because the distribution differs between labeled training set and validation set. So the labeled training set does not cover the full data distribution. We shall choose unlabeled data that best represents the full data distribution in order to improve the model. In this work, the author would like to develop representation-based active learning framework. A baseline approach that targets for selecting samples for better data representation is called core set. They treat initial data D0 and selected data D prime as k-centroids, and they want to select D prime such that all of the rest and sample data points are falling inside the delta S balls centered at each k-centroid. So it's like you are finding the best k clusters to represent the whole data distribution. The problem is that the distance between data points are measured by L2 norm. However, the LP distance suffers from curse of dimensionality when your input space is very high. This kind of curse of dimensionality is called distribution concentration phenomena. In high dimensional space, all the points are most of the time distant from one another. The distances to the nearest neighbors are actually close to the distance to the farthest neighbors. That is, the distance are all the same. For example, let's look at the histogram on the right. If we sample 250 points of unit length, then measure all the pairwise distances, then we can plot the histogram of distances. We can see that in 2-dimensional case, the distances are quite spread out. However, in 100-dimension cases, the distances between points are all the same. They are concentrated together. Thus, using Euclidean distance in high-dimensional case is not a good choice. Hello.
Please go now.
So instead of using a simple LP distance to measure distance between data, we instead train a deep learning model to automatically measure how different the data is from the labeled data pool. The key idea of this work is, firstly, they train a variational autoencoder model to represent data in latent space. Then they also train a discriminator model to distinguish labeled data and unlabeled data. Every time when we select unlabeled data. We select those that the discriminator think its confidence of unlabeled is high. That is, it is significantly different from labeled data in terms of distribution.
Please keep going on.
And I will briefly revisit the concept of variational autoencoder. To introduce variational autoencoder, we need to start with autoencoder.
Here, I have a question here. Maybe I asked a question too soon, but so here, will you please go back to the previous slide? Yeah, here just as you mentioned, there's a dimensionality curse for if we're using Euclidean distance. Now here, the VAE is trying to conduct or reduce dimensionality into a smaller dimension to address this problem. Am I right? So this is the role played by VAE, and that's all.
Yeah.
Okay, thanks.
And the discriminator here is actually trying to measure the distance between data in terms of the probability that it belongs to unlabeled or it belongs to labeled. Okay,
so if they would like to, so here the discriminator is basically the classifier. So it's just saying that the Euclid, even if we have a low dimensional space learned by the VAE, it will not using the Euclidean distance or even on this low dimensional space. It decided to train the discriminator to give a score.
Yeah. Later, they have an ablation study to show that adding the discriminator can better classify labeled versus unlabeled than defining a simple Washington distance on the latent space.
Maybe you can be more specific on what is Washington distance.
Oh,
it's very famous. I learned this term a lot, but I didn't go through the details.
So, because VAE will output a distribution instead of a fixed vector, to measure the distance between distribution, we cannot use the normal Euclidean distance, etc. So we use Washington. Washington is actually the Earth's modular distance. If you know about transportation problem, it will find an optimal way to transport all the mass from one distribution to another with the minimum cost. So
I somehow got a point, but if it is the transportation progress, isn't it mean that the first dimensions on the first dimension, because we using VAE, the intermediate representation is a distribution. Each dimension on the intermediate vector, intermediate representation is the dimension. It means that the dimension on the first, suppose giving two vector, let me write something.
It's a distribution.
V2, right? So there's dimensions. If we're using EMD to match these two vectors, is that possible that this dimension can match to this dimension? Is that possible?
Actually, it's not matching two vectors, but it's matching two distributions. You can imagine a bell curve in high dimensional space, and each point stands for a mass, right?
Each point stands for a variable, right?
Each point, because the high dimensional bell curve is actually the probability density function.
Yes.
So each point, actually, it's like a volume. It's like a mass volume. And then you want to transport this mass volume to another distribution. Then how do you dispatch it to different location of another distribution?
You're right, but in terms of mathematical form, so suppose we have 5 dimensions. Supposing we have 5 dimensions, each dimension corresponding a mu and a sigma, right? Each dimension.
You should view all these dimensions as a whole.
Okay, maybe I
high dimensional space.
Okay, I got it. So So
Yeah.
I haven't got it, but
So-
anyway, maybe I asked this question too soon. So let me go through the details of the
I will
presentation
not.
of
I will
autoencoding.
not go through the detail.
No, I understand. So
Yeah.
you
So
will have slides
if-
for the
If you
original
are
encoder.
interested, you can check.
Okay,
Maybe it's
sure.
hard to explain here.
Okay, so anyway, I understand. So the Washington distance is a way to calculate the to best match to optimize the distance between two distribution. But maybe
Yeah.
I go through more details on your next slides about
Does
the
it
variation.
like KR divergence, like mention the difference or distance between two distributions? Like
Yeah, it's like KL divergence, but it performs better than KL divergence.
If it is just the k-bus that KR divergence, it is just
It's like the function, like the goal.
You mean it had to have the same
goal
intention?
is like KL
Okay,
divergence.
the intention is
Yeah.
the same as KR divergence. But maybe we can be more specific on but later we can go through more details on how it's calculated and its underlying rationale. Okay, please keep going on.
Because that part is in the ablation study, so I will not explain in details. But if you're interested, you can check.
Read the paper. Yeah, that is a
Yeah.
very great practice. So for the presentations, we just present the abstract point of each paper, the rationale of each paper. If you're interested, so Ruofan will share the slides in the group, and then interested, even interest audience, maybe even me, will check the paper later. Okay, please go on.
I will first introduce what is autoencoder. So taking image data as an example, images usually have thousands of dimensions because each pixel is one dimension. So when we make decisions, for example, recognize which digit is inside the picture, we expect that there are many redundant pixels and unimportant pixels. For example, the black pixels around the digits does not affect our decision at all. So autoencoder first try to compress the high dimensional data into a low dimensional latent vector. During this compression, those redundant and noisy dimensions will be removed. A well-trained autoencoder expects Z to contain all the important information in X. To verify that Z has all what we need to reconstruct back to X, autoencoder has a second module called decoder. Decoder tries to reconstruct image from X. If the dimension reduction of autoencoder is effective, then we expect the reconstructed image is close to the original image, right?
Okay.
However, autoencoder actually suffers from overfitting. I don't know, can someone help me to explain why it suffers from overfitting? A hint here is if we consider the latent dimension is 1.
You want to point some audience here?
Maybe Yufen.
Hello, Yufen.
Hello, sorry, I didn't get it.
You didn't get the question or didn't get the answer?
Yeah, I didn't get the VAE.
Oh no,
Autoencoder.
Ruofan haven't introduced VAE. Ruofan just finished introducing AE. That means autoencoder. Have you ever heard about autoencoder?
Yeah, I heard about the autoencoder. I also heard about the VAE, but I didn't know much detail. I only know maybe that's a PZ for the VAE. It's a sorry, I don't know.
Okay, so maybe we find another audience.
Maybe Dr. Xiao.
Okay, just as you hint here, if if given the size of the latent dimension is only 1, so for every image, they will have, I mean, the hidden vector is 1. So actually, they will not have other information besides I mean, so they try to
Yeah, I try to memorize, right?
yeah, from only 1 dimension to the, I mean, to the original model. Yeah, decode it to the original model. So they,
I think it's close to my understanding. But before I give my comments, is there any other student or someone would like to comment on this question? Yeah, Xiaoling, what do you think about it? So, Ruofan has a slide saying that autoencoder, if they reduce the dimensionality to 1, and there is supposed to be an overfitting, and why this phenomenon would called overfitting? If Darren and Selby will have some idea, or you change the idea, you can just comment.
I think just like Ruofan just said, AE would try to like memorize, and VAE would add some randomness to it.
Yeah, my understanding is that we can just design a AE which memorize each images with its index. Then we recover its index back to its original images. So basically, the model learns nothing but memorize. So if there's a new images here, it will not work anymore. So, but this is just an extreme case.
Yeah, exactly. So if we reduce the latent dimension to 1, then we are not learning the latent vector, but we are just constructing a dictionary to map training images to some random case. So it's trying to memorize the image, but when during prediction I see a new image, then I cannot find the same image inside my dictionary. So it's overfitting.
But this extreme case is that if the dimension is dimensionality is 1, and if it construct a dictionary 1, 2, 3, and each one is an integer, right? Each one integer, but for
it can be anything.
But in practice it could be a float or double. So for example, the image reduced into 1 will be similar to the image reduced to 1.1 or 1.2. So they may still have some kind of the generalizability. But if we reduce the dimensionality too much, we do have the problem of information loss.
I got this, but why VAE didn't suffer this problem?
Maybe that is what Ruofan is going to do in this slide, right?
Okay.
Because VAE takes a Bayesian approach. It lets the output from encoder to be a distribution instead of a fixed vector. So if we have a distribution, it adds some flexibility and uncertainty to the output. And also, the distribution is called posterior, which means that we can have a prior for the latent vector Z. And having a prior can reduce overfitting because it's like adding a regularization.
So here maybe I can repeat Yufan's question. Suppose we using VAE to reduce an X into a one-dimensional vector. So we will have 2 parameters, mu and sigma, right? So we will, through mu and sigma, we will sample a random variable to reconstruct the neural model. And then maybe you can more specific or provide a more another detail or more another example and how this approach can allow us to avoid the overfitting phenomenon. Hello, I'm asking a question.
Hello.
Yeah, I'm asking a question.
Yeah, I need to exit the full screen mode.
To draw something, right?
Yeah. So it's like AE will output a point estimate, but VAE will output a distribution. So a point estimate tend to overfit, but if you output a distribution, that will reduce overfitting, right? Because you have some probability to take this value and take this value, etc.
All of these values required to be recovered as the original image. Right.
Yeah, should be.
Right, it should be.
Yeah.
Yeah, I think this is fairly clear. Okay, let's keep going.
Okay. A variation from VE is to combine VE with GAN. So from VE, we add the discriminator module to distinguish the reconstructed X prime and X. In this way, VE and the discriminator play a min-max game. On the one hand, VE tries to reconstruct X prime that is as close as X. But on the other hand, discriminator tries to distinguish X prime from X. So GAN is like an adversarial training opponent to VE, which can in turn improve the VE capability.
Okay, so GAN is just auxiliary, right? It's more like auxiliary component.
Auxiliary.
So discriminator will. So this progress wants the discriminator better and better, or the VAE get better or better.
Both.
Both.
But their goals are conflicting.
So
yeah,
why?
I think the ultimate goal, yes, during the process, both components will get better and better. But I think the final or the ultimate goal is to make allow us to have perfect VAE.
Yeah.
So the difference between this and the GAN, what's the difference between the VAE GAN and the GAN? Does this just change the generator to a VAE?
Yeah.
Okay.
Yeah, from the precision point of view, yes, they just replace GAN with the decoder, right? Yeah, you can see.
I have a question.
Please.
Oh, I see the next slide. Oh, I don't have question.
Okay.
So let us formally introduce the paper's framework.
Sorry, maybe can I? Does the paper mention that why they think they use VAE to to be the generator is better than the original, original GAN? Why they choose, or maybe why not directly use the GAN? Yeah.
If you use the original generator of GAN, then is your input an image or a hidden vector?
Yeah, the point is here. So the original GAN only have the component of the decoder, but here in this approach, in the center of this approach, they have both labeled data and unlabeled data.
Yeah.
They need a component to encode these images into a latent space so that it can be discriminated. And here, the generator part is just to play a role of having a perfect latent space to learn the perfect latent space. Here, I think the result of the generation in itself does not have does not have much to do with the overall.
Your background is noisy.
Hello?
Yeah, your
Is that-
background.
Is that better?
So someone's yelling at
Yeah.
Yeah. There's some children yelling outside my door. I can't do nothing about it. Maybe this micro is too sensitive now.
You
Maybe I
can
can.
actually set the noise level of Zoom.
Okay, I see.
Hmm.
Okay, I'll try. Please go on.
Yeah, so I think here, because discriminator is trying to discriminate unlabeled versus label instead of real image and generated image. So it will use the original data instead of randomly generate some data. Yeah.
Okay, got it. Thank you.
So first, let's look at the component here. We have a label data pool, and label data pool, and the initialized task learner, which is the model we want to improve, and the variational autoencoder plus a discriminator. First step is to select a batch from label data and select a batch from unlabeled data. When we select from unlabeled, we select those unlabeled data that the discriminator confidence is high. That means the current discriminator thinks it is very different from labeled data. Then we
Please go on. Please go on.
Then we compute the reconstruction loss and regularization loss for variational autoencoder. Because when we concatenating VE with discriminator, you can imagine the encoder part of VE serve as the generator of gain. So generator tries to fool discriminator. So we need to compute the generator loss. And then we update the weights in VE.
By the way, the generator loss, does the generator loss similar to reconstruction loss?
This part is reconstruction loss, but this part is the generator loss.
You mean is some noise on my part too?
Yeah.
All right, okay.
Noise, I can't hear.
You cannot hear my noise.
Yeah, I can't hear your.
Yeah, the noise level is too high.
Okay, so maybe let me check it again. Let me see. So let me try again. Is that better?
Yeah.
Is that
Yes.
Yeah.
So okay, please go on.
Next step is to compute discriminator loss and update.
Hi, Ruofan, could you please explain? I mean the previous two laws again. I didn't hear also. Sorry.
So this part is just the loss for variational autoencoder. So we have two kinds of data, right? Labeled data and unlabeled data. Then for both kind of data, we want it to have a low reconstruction loss. And we also put a regularization on prior.
Okay, the loss is over there.
Yeah. So the first row corresponds to the loss computation for the labeled data. Second row is the computation for unlabeled data. And if we look at first row, then the first term is the reconstruction loss. Second term is computing the KL divergence between the posterior and the prior. Yeah.
So another question, why don't we train the autoencoder based on raw data?
Oh, Because when you're doing training,
I'm sorry,
you need to process batch by batch.
I didn't get Dr. Lin's question.
What I mentioned is that why don't we try the process with first train on more.
Huh? I can't
Put that
hear.
on.
Well, I find myself, this is voice problem, so we didn't get
The voice
Voice
problem.
problem.
my voice is still, okay, hello, is that better?
Yeah.
You can keep going.
Huh?
You can keep going on.
Oh,
You can keep going if my voice is too faint for that.
So this part, actually the encoder part of VE serves as the generator of GAN. Therefore, the generator of GAN, we have a generator loss, which tries to fool the discriminator. It tries to make discriminator cannot distinguish labeled data and unlabeled data.
Hello, can you hear me? So yes, I understand for traditional GAN, the purpose again is to fool the discriminator. But here the input of the discriminator is the latent space, is the intermediate representation instead of the output of the generator, right? And in that case, how can the generator or how can the decoder to fool? How can the decoder fool the discriminator?
Encoder.
Oh, you're saying that encoder is going to fool the discriminator?
Yeah.
Okay. Why bother to fool it? Because once we have an encoder, it is just the embedding vector, and the discriminator.
Because you want to play the min-max game. So you treat the encoder part of VE as the generator of GAN.
It's to me, it's more like the organization of.
It's like you have some adversarial training on VE.
You
to
see
improve
here,
the
I still have a big
robustness.
confusion here. So I'm just looking at your graph. Here we have some samples from label set and have some samples of some label data, right? So then the discriminator is going to distinguish whether it's coming from label and unlabeled, right? So
first you reduce to latent space and then you feed it into
yeah, that's right. So once the discriminator finds it is unlabeled data, it's do nothing. When it's found unlabeled data, it's keep into the oracle and
it will find those that are more unlabeled, that the model think it is unlabeled, and then add it to the oracle. And then this selected unlabeled become the labeled data. So in every active learning cycle, they try to select those unlabeled data that haven't been included in label sets.
So basically, it's going to learn which unlabeled data set, unlabeled samples is more similar to those label sets.
Yeah.
I have another question here. Because they are using representation layers from the VAE, but can we use the representation from the task model? I mean the model.
The subject model.
Yeah, the subject model.
I think can. For example, you can share the encoder for VAE and your task learner. For task learner, you just append some dense layer, then output the prediction.
I think it's very hard to say, but one advantage to using the variational encoder is that the latent space is more representative because there's a reconstruction loss to make sure that the low latent space contains enough information to recover the original image.
Oh, but there is a problem if you use encoder in task learner, because encoder has variation. It will output a distribution, so you need to sample a latent vector z, then feed into task learner.
But let's say, what if we put the gap layer from the ResNet as the representation embedding to the discriminator?
They still want distribution instead of
so here I think
fixed layer.
I think my explanation is that the gap layer or the another embedding in task learner may not be a reliable representation. It is a good, maybe it is a good representation for the current task, but here we are looking to a more generalized representation, and here autoencoder allow us to learn a more general representation because this representation contains all the information of the images, so that the proof is that there is a decoding which can recover from this clear representation. But if the embedding in the task learner, it may not do the same, which means that it may lose some of the information based on its embedding.
Oh, yeah.
Have my
I get your.
maybe back to my previous question. So here there is the iterative process, right? So if I'm the one who designed the approach, maybe there's no need to have an interaction. We just giving the label data and label data. We just run the variational encoder. And during the learning, there is no interaction with the discriminator. So we already have the intermediate representation. And then we feed it into intermediate representations into discriminator. And all the stuff is one shot. There's no need to be such an interaction. So is that the interaction is that given the batch, we learn the autoencoder using discriminator to do this. And I think C may not, from my point of view, that interaction may not necessary. We just need to train the autoencoder to learn the representation of all the data, both labeled and unlabeled data. And after that, we already have the representation there, right? We already learned the encoder to represent all the images. And after that, we feed them into the discriminator. Is that possible?
I think they still want to learn VAE and discriminator together, because discriminator is like adversarial part of, it's adding an adversarial training to VAE. So you want to jointly evolve those two of them.
Let me think about it. So the adversary part is that once it is considered a label. So here I have a question. If a labeled images is classified as a label,
then you will not select. You will not select and you will not label them. So they still remain in the unlabeled set.
It will not be duplicated.
Yeah. It will not, because every time you will like sample hard samples, you will select hard samples.
Okay.
Oh.
Okay. For the iterations, so the whole process is one iteration. Let me write a flow here. So this flow is for one iteration, right? For each E.
Yeah.
For each E. So and each E is an apple. Okay, so that's the epoch means that so each epoch means that I still have a question here. So the samples, right? So why not we feed all the samples to learn the variation? into the VAE and why we need to sample? That means we learn a full thing.
I don't know, maybe you
one
have
shot.
limited computational resources and you have several models to train, so you cannot afford feeding all of the data. You can only do batch.
Why
learning.
not? For example, the label data could be 10K, the unlabeled data could be 100K, right?
But even for that, you need to like divide them into batches and then.
Yes, we just reshuffle all of the data into batches and train out encoder, or train out the original encoder. And after that, we use it to learn label and label in the selected view, and still connect the context. And why do we need the sample? But maybe for each
I
batch,
can't
for each
answer
batch,
this question.
maybe. So here, I think, so the term they use is epoch. Usually, epoch is the definition for training to pass the whole data set. Right. So the epoch means the pass for the whole data set. But if we're using sample, which is more like one batch. For each batch, you need to calculate the loss, and then update the distributional thing. Okay, let's maybe leave these questions here.
May I check that the model use YL? I mean
YL.
YL, yeah, in the VAE gain.
Sorry, what is YL?
For example, the second line sample XL and YL. So I'm wondering, yeah, does the YL use?
No, they do not need YL. That's only in task learner you need YL.
Okay, thank you.
Then the last step is to update the task learner. So task learner is co-evolved with VAE discriminator. All the models are trained together.
Any questions for this process? Maybe we can spend 1 or 2 minutes on these slides.
How to update the decoder of the VAE?
Oh, it's this part, this reconstruction loss part.
So it's different from the GAN because the GAN use the output of the decoder to train the to input the discriminator. Here I use the latent space to input to the discriminator. Is it right?
Yeah.
Okay.
Then can you explain this equation 2 one more time?
So here I'm trying to fool the discriminator, which means I will make the discriminator confidence on label data to be
Here there's no
large.
difference between label and non-label.
Oh, ZL is labeled and ZU is from unlabeled.
Yeah. So
it's from encoder, so they are all false. They are all adversary sample. That is right.
They are from original data.
So
there's no adversarial, yeah. Because it's from original data, so you don't need to generate some random image.
Sorry, can I just check? What's the discriminator? The discriminator is like another model that just determines whether it's unlabeled or labeled, is it?
Yeah, it's like a classifier.
So it's also is there error? Is there a possibility of an error in the discriminator?
Yeah, could be.
So if it classified incorrectly, what's the implication?
Yeah.
Yeah, what's the implication if the discriminator classifies it incorrectly? That means it classifies an unlabeled data as labeled or something like that.
That means the discriminator is immature. But when you select data, you still choose to trust the discriminator because you will only select those data with high confidence of unlabeled. So you think those high confidence are the reliable prediction from the discriminator. It doesn't matter that you make a prediction on some low uncertainty data.
I'm still lingering around equation 2. Can I interpret equation 2 as it wants the VAE to output the same, not the same, but to treat labeled data and unlabeled data as the same. Yeah.
Yeah. And you can compare with the discriminator loss. So actually, it's just flipping the sign of the second term.
Maybe
Right?
can you quickly modify to align all these equations all together? So I'm just reading on your slides, just switch back. Can you quickly edit your slides so we can compare all the equations or the business function together?
So here you
And
can
also
see
maybe you can also
the
include
first
the
term.
maybe also include the equation 1.
But equation 1 is rather independent from these two, because equation 1 is just the original VE loss with a beta as a trade-off parameter.
Okay.
Equation 2 and 3 are two conflicting goals, right? The first term of these two laws are the same, but the second term have a minus sign here, but here is positive sign. Because for discriminator, I still want to suppress the confidence of an unlabeled image predicted as labeled. But for VE, I want to make unlabeled being indistinguishable from labeled data.
Do you think about this? It just want to make the discriminator more robust.
I want to make the
right, you can see the discriminator do nothing. The discriminator will do nothing about the encoder, right? It will not. It will not. Right?
It will because this Q is output from the encoder. So if you trace back, then it will be trace back to the encoder.
So the discriminator will try to.
But when you train the discriminator, you freeze the encoder. Yeah.
I think it will not. But the encoder is not a.
Encoder is like the generator part of GAN. Yeah.
So he didn't use the output of the decoder because the dimension curse.
Yeah, I think so. Maybe it's easier to distinguish from latent vector.
Okay.
Maybe let's move forward because we have another presentation later. But it's a very good discussion. Ruofan, maybe you can share the slides later for us to further digest. I think there's still, I get a big picture, so I think, but I still have some details to digest. Okay, let's move forward.
So maybe you are not clear about where you get and where you first see this. Maybe it's a bit confusing, but you
I think
can
it
then
needs I
translate.
still need a few minutes
Oh.
maybe to fully digest it. I think I'm probably not, I think we did not spend time here. And I do have some concerns of that about the contradictory, or they need to and how the discriminated values groups encoder and encoder how discriminated discriminate. I still have some concerns about the situation because again, things they may not that necessarily case, but I haven't got the full details. Let's keep going on. Okay, is there another question here? Let's go through the experiment.
So for the experiment, we initialize the labeled pool with 10% of training set, and the budget size per batch is equal to 5% of training data set. So here you can see when we do the experiment evaluation, we do not interact with Oracle because that is not convenient. So when we do experiment evaluation, we just use those training data. Then we evaluate the AL framework on two kinds of benchmarks. The first one is image classification. Second one is image segmentation. So the blue line is this paper's work VAL. The rest are baselines. We can see that it outperforms the rest baseline on validation data set, given the same labeling budget.
So there's 4 data set. So this is validation, right? So all 4 images are validation. But there's no, okay, but it makes no sense to look into the training set.
Yeah.
But this against the improvement, a little incremental.
But compared to baseline, it's better, then it's better.
For theta 10s, it seems like the quartet they still have a very good performance.
Yeah.
But for cloud tech and the internet, it does increase the advantage. Okay.
Maybe when the number of classes grow, then VAL has better performance.
The number of what?
The number of classes to classify. Sapphire 10 only have 10 classes.
Okay. Okay, keep going.
This is image segmentation. For image segmentation, the validation accuracy is mean IOU instead of classification accuracy, because segmentation is trying to predict some mask. Anyway, it is better than baseline. Yeah.
Okay.
So here they are doing ablation study to test each individual component. The first study is they remove VAE and let discriminator to discriminate based on the original image space. They find that discriminator has an overfitting problem. It just tried to memorize the data. So they show. So they see that VAE are playing an effective min-max game to avoid the overfitting phenomenon in discriminator. The second study is they freeze VAE but only train discriminator. They find that it performed better than the first ablation study but have similar performance than random sampling. So they say
better than one. Okay.
Better than first.
Better than eliminating the setting of when we eliminate the VAE.
So they say we really need to train a good VAE to project onto latent space.
Do you mean they like first train a VAE and then froze it.
Yeah. And then do not.
Only
So
train
that is my gut feeling. That is
Oh.
what I suggested previously, saying that if we just freeze VAE,
Mm,
then we try to discriminate,
mm.
and it is no good.
Because if you are playing the min-max game, then VAE becomes better, discriminator becomes better, then VAE becomes better again. So it's like two opponents are fighting so that each individual component are become stronger and stronger.
Mhm.
Mm.
When is this paper published?
2019. 2019.
2 years ago.
Okay, because once I do a project, course project, I also use this idea. So I think it's not very new
Effective.
idea. Yeah,
Oh.
new idea
Mm,
to use VAE and GAN.
mm.
Your course project still on active learning?
No, we use this architecture VAE and GAN. Use VAE to generate some representation, and this representation, we think these representation are false, and the original is new and the input to the GAN. So
Input to the GAN.
yeah,
Okay.
because GAN need one false representation and one true representation, and originally it used the noise to generate the false representation, and the new ideas is that use the VAE to generate the false representation.
Mm.
Yeah, so this is very not very new ideas, I think.
But I think it's an application paper. It tries to apply this technique in active learning. Then yeah. The third study is to completely eliminate discriminator, but instead use the Washington distance. It used one type of Washington distance called two Washington distance.
What's the difference between one versus distance and two word?
I think maybe the difference is in this power, because here they use two.
Oh, okay.
Yeah. And then they find the original VAE performs better than all these ablation studies.
Which one is the Washington distance?
Orange.
Okay. Let me have a check. Okay, so but the Washington distance that has already outperformed the rest. Okay.
Yeah. Oh, and one of the experiments I find it very interesting is they try to test VAL robustness against noisy oracle. Means that oracle sometimes give erroneous labels. They randomly change the ground truth labels to have incorrect label, but still within the same superclass. And they find that given the same error percentage, VAE can outperform the baseline. So to read this graph, we shall read this tree line as one group, and this tree line as one group, and this as one group, because they are of the same error percentage. And this blue and red and pink lines are VAL. The rest are baselines. You can see that as the error percentage increase, actually VAL has very similar performance as baselines. but still better. Okay.
Sorry, may I ask the y-axis, the mean accuracy is whose accuracy? The
Validation accuracy.
okay, thank you.
The person accuracy, so it's around, since here the mean accuracy, the mean say around experimental multiple times.
Yeah. The takeaway here is it developed VE again to effectively learn the latent space representation and discriminate the distribution between labeled data and unlabeled data to help active learning. Yeah.
Okay, so thanks, Ruofan. Is there any question here? If no further questions, let's proceed to the presentation of Yuchen. Ruofan, please share the slides.
Okay, hi. So today I'll be presenting on this paper called Fast Concurrency Debugging with Parallel Differential Analysis. Yep. So the paper is by Liu Zhen. She's a PhD student in Texas, and her supervisor is Prof. Jeff Huang, also from Texas A&M University. Okay, so so the background for this is that the concurrency bugs are easy to introduce but hard to detect. And most of the tools that detect concurrency bugs are designed for the late phases of software development, such as testing or after production. So example of that would be like the Kairouks paper I shared last week. So that's for post-mortem analysis. And so what the tool they developed is that it does incremental analysis. It's a fast concurrency analysis framework to find the bugs interactively during development. Okay, so basically, I'll be going through these parts: the design and implementation of their analysis framework, the parallel differential algorithms that they used to analyze the current programs, and how they detect deadlocks. Okay, so for motivating example, so imagine that we are this developer, right? And then we are writing code that spans these two threads. And then I make an insertion here where I access the variable X, and now I'm trying to assign some value to it. So what happens here is that there is a race condition, right? Because I'm accessing X2 without obtaining this L1 lock. Yep. So
maybe can you draw the flow, the execution flow when the race condition happens, or maybe you can briefly explain what is a lock.
Right. Okay. So a lock is basically just some object, right? That you're supposed to you can have like certain operations on it, mainly the acquire and release. So what happens when you acquire a lock is that other programs or threads that try to acquire the same lock will get blocked, so they will stop. And then when you release it, then maybe some other thread that is queuing on the lock will get unblocked, and then they will go ahead and acquire the lock. So of course, usually what we do is that there's some critical area, right, where a program is accessing a shared memory, and when I am operating in this area, like you don't want other threads to come in and also touch the data here. And so that's when you have like all the concurrency problems. So
the ultimate goal is that we just want to parallel the computations. We need to multiple threads run in parallel. But if we want these two threads or process need to synchronize each other, we somehow need you, for example, we need one thread to stop one thread to be suspended and another thread to be executed. And the way to synchronize these threads is using just as you can mention as log. Basically, the log means that if a thread, here you can consider a log is a resource, and this resource is more like a guard. If one thread has already taken the resources, these resources is used to guard the execution of certain critical sections. Relating with another color. So we call this is a critical section. So here, when during execution, multiple threads are trying to compete for these resources so that they can enter or execute the code in the critical section. And the thread, if one thread has taken the resources and started execution in the critical section, the other thread have to wait outside the have to wait on such a lock until the thread, the previous thread finish the execution of the critical section. Then the second thread or the other thread will if there's another thread will be compete for such a resource again, and then can execute the critical section. So this is the basic idea of lock. The lock is going to is used to guard is the resources guarding a critical section, and the threads, whatever threads have taken the lock or acquired lock, it gains the authority or gain the right to execute the critical section, and the thread then to get the resources have to wait on such a lock until the one buying the lock finishes execution, then release the lock. So this is basically the idea of lock. And Yuchen, maybe you can further explain how the race condition happens.
How the race condition happens. Okay, so as you can see, right, perhaps our
So you can
thread
see
one,
in stretch one, there are two locks, L1 and L2, right?
yeah. So there's lock 1 and lock 2, but in thread 2, there's only lock 2, right? So our thread 1 can go in and then it modifies your X here. And well, there's nothing stopping thread 2 from also executing and therefore modifying this variable X at the same time. So when this happens, then obviously like there can be interleaving executions, and then at the final state here, and after these two statements, we don't know whether X is going to be 1 or 2. There's no way to tell. So this is where there's a data race. And so the goal of D4 is to like highlight these points to the user. And so let's say that I try to fix this data race, right, by introducing another lock over here. And what happens now is that there's now a deadlock. So we have this execution. Perhaps thread 1 goes into here and acquires lock 1. And then thread 2 carries on and then acquires lock 2. So we see now that thread 1 has lock 1 and then thread 2 has lock 2. And then now we are stuck because if thread 1 tries to acquire lock 2, it'll be stuck because it's already acquired by thread 2, right? And then from thread 2, if I try to acquire lock 1, it's already acquired by thread 1. So now both processes, both threads are stuck and there's no progress.
Okay, excellent explanation. So here the point is a random fix of the race conditions is likely to introduce a deadlock condition. So the default solution is going to, will they recommend a remedy for the race condition?
Oh no, they don't. They just highlight these offending
I
lines.
got it. So your example is that once the race conditions or the deadlock condition happens, it just highlights the problem.
Yep. Okay, so let's carry on. Right, so D4 has three main parts. So the main parts are the pointer analysis graph. A static happens before a graph, and this component that does the data race and deadlock detection. So this is the overall kind of architecture, I guess, of the whole system. So what they did is they separate the analysis framework from the client machine. So this is supposed to be in the cloud, right? So that's one of the assumptions. And then each change in your code is sent via some like HTTP request maybe, and then it's sent to various workers that.
So it means that the development environment is cloud environment.
Not really. The development environment is whatever the user is using, right? But basically, the changes
so there's
is
a bugging,
processed.
there's a bugging framework is actually deployed on the cloud.
Yeah.
Or deployed on another server.
Yeah, yeah. So it lives outside of the development environment. Yeah. Okay, so the main point to focus on is still like these three parts, right? So what happens is that the change in statement first goes through the pointer analysis. So we'll go into depth about that later, but basically they have a graph to represent all the pointer relationships, and then for each change in statement, they update the graph, and then the updated change in the graph is also piped as the input to the happens before analysis graph. So from here, there's a change, and then this change will be used together with the change from the pointer analysis graph to detect the data race and deadlocks. So that's the flow of information. Okay,
So I think you do have some analysis explanation for what is pointer analysis and what is happens before analysis. Right?
Yep. So here we are on the pointer analysis, and this is basically how they represent the underlying data structure for the pointer assignments. So in this graph, each node is each pointer node is a pointer or reference variable. So okay. So it's something like this. So these are your pointer nodes, and then there are also object nodes. So the object nodes denote the memory locations of the objects. Yeah. So this is an example, right? So let's say that we have a new T, and then this is object one. So when I assign object one to X, it forms an arrow here. So that's the relation, that's the edge. The edge is a subset relation of the points to set. So what's a points to set? The points to set is a set of object nodes that the pointer node may point to. So in this case, O1 points, there's an edge from O1 to X, and then there is an edge from O2 to Y. So this is here, and then afterwards we assign X to Y, right? So now there's an edge here. And here the points to set for X would be O1, and then the points to set for Y would be O1 and O2. So, okay, any questions so far?
Yeah, I think Yuchen make a perfect explanation here. So during the program analysis technique, actually for static analysis, so for program analysis technique usually consists of static analysis and then static analysis. For static analysis, to only analyze the code per se, and for dynamic analysis, we need to run the program and run the program to observe the dynamic behavior. So during the static analysis, there is a very classical, very classical topics is called pointer analysis. But whatever C++, Java, and Python, sometimes despite we have two variables or two simple x, but during the execution, it is likely that this x is just the alias of y, or vice versa. And sometimes we have to know this information to make the sound analysis. For example, when we find the final output is 0, which we know it is not a correct, it's not a correct answer. We need to know where these where this variable, where in the code, the variable, the final output for the variable, maybe x, is assigned with a value of 0. So we need to check all the assignment. But sometimes, if we do not have the pointer analysis, we can only look at the output x. However, sometimes the y will be assigned will point to the same memory location of x. And if another possible is manipulated y, it is actually significantly different to manipulate the value of x. So in this case, the point analysis is going to go through all the process to analyzing all the A-list variables to the classification x, so that our analysis result will be more complete. Okay.
Okay, so I shall carry on. All right, okay, so this is what happens when there are additions, right? So as we said, there are changes in statements. And say that I add in a new line, right? So I have, in this case, there is x. So x may point to some objects, right? And then we have y. And y also points to some objects. And then we add in this line where we go x equals z. Yeah, so what happens is, well, actually this is x equals y equals x. Okay, so say that we add in this line, we'll just basically add in this edge from z to x. And then following this change, right, we just look at all the points to objects in z, and then we add it to the set of points to objects in x.
So the point to set will be increased by such an analysis.
Sorry?
So here you're talking about incremental analysis of point analysis.
Yeah.
So once we see any fold change, we're going to increment or modify the original point to graph based on the fold difference, right?
Yeah.
So now
yeah,
we're
yeah.
talking about addition. Okay.
Yeah. So I guess you can see that it's pretty straightforward. We just find the change, and then we kind of just do like a reachability check, right? We see like all the affected nodes downstream from this change, and then we just update all the points to like all the objects in the set. Yeah. So addition is quite straightforward. Then the problem comes when we have a deletion. So if we delete an edge, right, then there's a lot of propagations, and then we have to kind of check each one, like, should we keep the same or should we like delete the objects from the set? So there are two algorithms in their past work that does this. So one is reachability based and one is reset and compute. And for both, right, they are not that good. So we'll talk about why. So for the reset and compute, basically we will find all the affected nodes and then we set their points to empty, and then we'll recompute whether so we'll recompute. So actually,
so there is almost more like it's not a incremental analysis, just reconstruct the graph again, right? Repropagated, it's repropagated the graph again.
Yeah. But actually, in either case, you still need to do the propagation, right? Even if it's incremental.
Yes.
Yeah. Okay. Yeah, but
for the former case, we only need to propagate a limited number of object, right?
Yes.
But for here, if we delete it, we need to calculate what need to be removed from the pointer set of each variable.
Yep. Okay, so I'll run through an example on this graph. So we can see here that the points to set here is 0, 01, and then from over here, this is 01 and 02 originally, right? This at first, right? So this is also 01 and 02, and then over here is also 01 and 02. Okay, so when we delete it, then what the algorithm does is that it will first look at the affected nodes, which is Y and Z and W. So it will just set all of them to empty first. Right, and then afterwards it will trace back from here. So from Y, now it's now the points to set is 02. And then from here, this one is also 02. And then from here, actually, it's a union of 01 and 02. So it's actually like the same, right? It's the same as the original. So obviously the problem here is that now there's a redundant computation, which is why it's slow. Okay, so an alternative is that we do a reachability-based algorithm. So for reachability-based, we look at the affected pointer nodes, and then we check if our node is still reachable from X. And if it is reachable, then there's no change in the points to set. So we end it there. But if there is, then we need to find the objects to remove. So for all the objects in my points to set of X, we check if that object is reachable to P. And then we repeat, you've got to propagate the change, right?
So basically, it's going to see whether these given variable is still reachable by the original variable, right?
Original variable. Yeah.
So here P is still reachable from X. So what if so it still need to have the difference analysis. So here this example is simple. It's just to remove the edge between X and Y. But in some extreme case, the variable X itself will be removed.
Yes. So if we remove a variable X, then that will just constitute removing this edge, right?
And the next edge, and all the edges rated by X will be removed.
Yeah. Yep. Okay. So, shall I run through this?
Sure.
So okay. So, for example, we see that we remove this edge, right? So our points to set now is so we fall into this loop and then we check. So X has only 01. And then now we're at Y. So we see if 01 can reach Y. So we have to do like a DFS from here. And see that, okay, actually it's not. So we remove the object. So from 02 and 01, we remove this. Right. Yeah. So now since this is removed, now we have to check the neighbors for Y. So for Z, we check once again if all the in this object set whether it's reachable. So 01 is now no longer reachable. So now we remove it also. So now it's 01 and 02.
We need to check the reachability. Isn't very, so it just seems very slow.
Yeah. So this one, okay, we see that X still reach Y, so there's no change. So it's still 01 and 02. Yeah, so the question is, what's the worst time complexity in such a case? Okay, I don't know.
Yeah, maybe you can check the audience and ask one of them to answer the question. I think this is supposed to be a tough one.
Yeah, maybe Xiangwei.
Xiangwei.
Yeah, okay. Let me think. Landing towards n power n.
N power n.
Yeah.
How do you calculate such a complexity?
Yeah, let me consider. Because for each of the nodes, it will have to look at their neighbor nodes, right? So if you,
So I thought about
yeah,
it. So maybe we can start with some simple calculation. So given a graph with n nodes, and we giving two nodes P and Q. What is the complexity to calculate the reachability from P to Q? So maybe we need to start with this complexity calculation, right? Suppose we make the find myself still forgot the complexity. Let's see the C. So suppose the complexity is C, and then we calculate this one. So because for all objects, so PDX is change, right? What does PDX stand for?
This points to set. So PTSX is 01, right, in this case.
Okay. So check this reachable and repeatable order. So this one supposed to be C times N, right? So by right. So just for area and to check this repeatability. And also, we can keep going on.
Yeah, so that's basically the answer. So it's if you take the size of the PAG as as the variable, right, then it's linear with respect to the size of PAG. And I guess if I were to do it, it will be something like where M is the number of objects in the points to set, and then the time complexity would be something like M of V plus E, right? Where V and E are the number of vertex and edges in the graph. Okay, so yeah, so the main problem of why it's slow is because of this. It's because of the graph traversal. Because in the worst case, it's going to go traverse the whole graph, and it's also in the best case, right? You can parallelize the different objects. So let's say that if my X has objects 1, 2, 3, then I can check the reachability of 1, 2, and 3 in parallel. But once again, it's still linear with respect to the whole size of the graph, PAG graph. Okay. Now we reach the second part. The second part is the static happens before graph. So static happens before graph.
Oh, by the way, so there's also provided solutions for, because it's saying that the reachability, both reachability and the compute solutions are satisfactory. So there's also provided a solution for this situation.
Yes. So this is the previous
work, right?
Yeah, existing work, and then they added on to that to make it more efficient, and that's the main contribution for this paper. Yeah. Okay, so some more background. The static happens before. So this is basically just, you can kind of look at it like the same the same kind of this kind of representation, right? So each node is some event, and then there is an edge for some special nodes, like when you start a thread. So there will be this happen before relation, right? This edge will represent the happen before relation for these two threads. So yeah, and in this case, M1 is actually a method call. So these two events are in the method call, and these two events are in method call too. So you can see that actually there's a repeat between here and here. So they don't have like a more compact representation for such a graph. And that's also one of the reasons why the previous work is not as fast, because if we want to update the definition of a method, so we change some statement in the method, now we have to find all the places where this method occurs, and then we have to change that. yeah, so updating the statements are very expensive.
I think Darren is asking a question is how SHP graph is generated.
How is it generated? Okay, so there's a rule for it. Okay, let me bring this up. So there's a table for each statement, right? So each statement, if it corresponds to some rule, then it will follow the nodes for it. So for example, okay, so let's say that there's an assignment, and then there will be such a right node for corresponding to this statement. So, and if such statements like this, then there will be this node. Yeah, etc., etc. So these are the nodes, and then this is the edges in the graph. So let's say that I call, right? Then such a call will have this call node, and then there will be edge from the call node to the first node of the method. And then it goes on, and then, yeah. And then there will be another edge from this to the next node.
Okay, maybe I summarize the rules as follows. Basically, it goes through each code statement, and some code statement will be used to construct a node in the graph, and some relations, for example, when we invoke functions, or if we start organizations, and these will cause, we will construct a between the nodes, and finally we will construct such a graph. So this is somehow a superset of the core graph, right? So here, suppose, but anyway, here I'm looking at T1 and T2. For T1, there's method 1 and method 2, but is there a core graph there, or we just invite the content of the method into a certain thread? So based on your graph, it seems that each node is actually a thread, right? Each node is just thread. Each node is just a thread.
Right, this box, right? Yeah.
Yeah. So what is the definition of this graph? Does each node is corresponding to one thread? And the age between the thread means the fork relation. But just if I read it from your graph, I can just have such a interpretation.
Actually, this is more of abstract. I just group it like that for understandability, because by definition each node is a statement here, right? Yeah, so actually this is just to group them all together.
So if right x is the node, so is there age between right x and right y?
Yeah, so based on the definitions of the paper, right, they don't say, but definitely I feel like you have to have a happens before relationship. If not, you can't like compare between these two nodes, for example.
Yeah, so let me rephrase. I think Darren asked a very good question about the definition of the graph. So basically, for the graph, it only care about a few limited events like read, write, call, etc. And the goal of the graph is going to organize or present which event happens before which other events. So this is basically what the graph tells us. In order to construct such a graph, we have to define a few rules to define the interested nodes and the relation between interested nodes. And for Yuchen's presentation, it's just showing 3 threads here, or just as Yuchen mentioned, understandability.
Yep.
Yeah, maybe you can brief 1 or 2 conferences once we construct such a reference before, and how will be used. Maybe I asked these questions too soon, but definitely we already have two complex structure. One is the point analysis graph. So they constructed all the dependencies or the alias of the variable, the potential alias variable. And here we have another complex graph called happens before graph describing the happens before relation between the events. And later you will mention how these two data structure will be used. Right.
Yep. Yep.
But anyway, so I think you did a very perfect presentation today. But I think I will give comments is that if you can better improve presentation, you can provide it now. So if we want to analyze the, of course, I think you just organize the presentation based on how the paper is presented. But later you can show that the rationale. So if we want to know the data race conditions and the data coverage and what kind of information will be used. In order to gain such information, we need to construct two graphs, and then you can go through it. It is more conformed to the human situation. But anyway, that's my comments. Please keep going on.
Okay, yeah, that's true. Okay, so main contributions by the paper. So there will be, so we improve the incremental algorithms for pointer analysis, and also we come up with a new representation of the happens before graph to minimize on space, basically.
So the overall contribution is just for improving pointer analysis and happens before analysis.
Yeah.
So that's all.
Yeah.
Actually, okay, so their title is called FAST, right? So FAST concurrent. So that basically it's just the efficiency improvement work.
Yeah, yeah. So actually, like a lot of the foundation is being set by their previous paper that like uses those previous algorithms.
Okay.
Okay. So these two, and then they have a small part about how they turned it into a client-server architecture, but that's not really the main focus. Okay, so so let's look at how we can improve the pointer analysis. So firstly, as we can see, the addition is quite fast, right? For an addition, it's quite straightforward, and like you can't really improve on it. But for deletion, that's where it's a lot slower. So the main result for this paper is that for deletion, now we only need to check the neighbors of the affected node when we delete an edge. So, and why is this so? So there will be a few properties and theorems to explain this. Now, firstly, there's an assumption, and the assumption is that your pointer analysis graph is acyclic. And this works because in the case of like cycles, right, there's a strongly connected component. And for a strongly connected component, you can actually just collapse it into one node. Yeah, and we don't really have to care much about it. So let's go on. Okay, so the first property is this incoming neighbor property. Actually, like it's quite straightforward. So if Q has an incoming neighbor R, right? So R points to Q, and then inside R is O. Then the O can reach R without going through Q. So it's quite straightforward because since O is in R, then it either goes straight to R or it goes somehow to R to Q and then from Q back to R, right? Because based on the setting, then like we assume there's no cycle, so this cannot be true. So basically there's a direct link from O to R. Yeah, that's all for this property.
So you're saying that O can reach R.
Yeah, it's just saying that O can reach R.
Okay. Okay. Oh, so okay, your point is okay. So, but what if O is still the neighbor? Q is still part of O. Well, it's a can definition.
Yeah, yeah. So, yeah.
Okay.
I feel like this property just like sets the reasoning for the theorem that comes later. Okay, so now consider the case where P to Q is removed. So once again, there's a incoming neighbor R that points to Q. Okay, so if we remove this, right, then whether or not we remove O from Q will just depend on whether there are incoming neighbors of Q that already has O.
Okay.
Yeah, so actually, is there any questions about this part? We don't need to go into too much detail.
Okay, so I have no questions here.
Yep. Okay, now the second is the outgoing neighbors property. So this helps with parallelizing like the algorithm. And it's kind of also an extension of the previous theorem. So let's say that Q has an outgoing neighbor W, and then W has an incoming neighbor R, and then O is in R. O is in the points to set of R. So then there are only two ways for O to reach R, right? Either it goes to R directly without passing through Q, or it passes through Q and then it reaches R. Okay, so once again, this is just, yeah.
Straightforward.
Yeah, it's quite straightforward. And so how it's useful, right, is that when you propagate a change to a node, it's sufficient to check the other incoming neighbors of that node. So if the points to set of any incoming neighbor contains a change, we can basically skip the node. And so why this works, right, is that say we remove Q to W, we remove this edge, then obviously O is still in W, right? So once we check that the O is also in R, then now we don't have to remove the O from W. But in this other case, if you think about it like checking it concurrently, right? So if we check, so there's like two steps, right? We can finish this one first, and then we see if W has O, or we do this one first. Okay, so let's consider the first case. So let's say that we are checking this part now, and then R still has O, right? And then when we remove this, so when we check the incoming neighbors of W, W has O, and then we keep it, right? And yes, and this is correct.
Yeah,
And
but what if there's another variable x, and this x is O, and this link is also be removed, then the information for R is not reliable anymore.
If there is an X that has O, then O must somehow go to X, right?
Yes, and the link between X and R has been removed by the evolution, by the co-evolution. So in this case, the R itself is not reliable.
Let me sequentialize this.
The point is that we only looking to 1 degree neighbor, but the 1 degree neighbor can still be affected by this 2 degree neighbors. And the change may not only part of 1 degree neighbor and 2 degree neighbors. In that case, the information we get from this 1 degree neighbor may not be reliable anymore.
But actually, it suffices to check the 1 degree neighbor, because later on there's this change consistent property.
Yeah,
and
maybe you can propagate a change. For example, if we are analyzing, for example, if we remove the degree, we can first start with the 1 degree neighbor, and maybe for the first iteration, the O is still kept, right? O is still kept, but after a few iteration of propagation, we will find that the R will not have the object O anymore, then we will update the O in W.
Yeah, that's basically how the algorithm works, and it's provable also. Yeah, so eventually, right, we will check where actually there will be a case where we check and then we see that O is not in R, and then all the neighbors of W doesn't have O, then we will remove it.
So this more like graph set iteration algorithms, and the algorithm will keep iteration of the whole graph until the pointer set converge. Right.
Actually, it's more efficient than that. Okay, so we'll
Okay,
go on,
okay.
and then I'll show you the.
Okay.
I'll show you there's one more change consistent property. Okay, so for an edge addition or deletion, if the change propagates to a node more than once, then the effect of the change must be the same. So as long as it's changed, then that's the end of the change already. So the smallest example, right, is let's say that we have some P, right, and then the P changed, and then there are two different paths to R1 and R2, such that when R1 and R2 like points back to Q, the change propagated in here is that it includes O, and inside here it does not. Okay, does that make sense?
Maybe I didn't get the assumption of the example. So P is a variable, P, R, Q are variable. And what is their point to object or point to set? The point to set is O.
Actually, it doesn't matter.
It doesn't matter. So suppose the point to set of R2 is O, and which part of the graph has been changed?
It's somewhere inside here. Or maybe like this.
Or deletion.
Maybe like this, right? So this one changed. So Q, there's some delta here, right? So there's either addition or deletion of O's inside here. And then because this one changed, then all the neighbors of P will also have some change, right?
I got it. So the point is that there's no need to propagate it, or you just need to propagate it once. If Q is reachable by P from multiple passes.
It's saying that even with multiple passes,
Yeah, so, I'm saying that. Yeah, I'm just saying that if there are multiple passes from P to Q, but we just need to conduct propagation for once instead of twice.
Yes, yeah. So let's look from the perspective of delta 1, right? So let's say that this is a minus O. So we remove O from the set from the points to set of R1, right? So let's say that we remove this, and then we will follow the checking neighbors part, right? So we see that Q actually has a neighbor R2 that has O. So Q will not remove the O object in the set. Yeah, and let's say that this change, whatever this change is, it will not include O because O is already in the points to set of this R2. Yeah, so whatever this change, it will just apply properly, and then it does not matter that R1 does not have O, right? Because this change does not include O anyway. So you can see that regardless of whether delta 1 comes to Q first or delta 2 goes to Q first, yeah, the change will be the same. Okay. So that's why we can parallelize. And what happens? Oh, I think maybe I skipped a few slides, but basically that's the algorithm. So for any change, we see, like, we just check the incoming neighbors for this affected set, and then we will update it, right? So if there is an update, we simply put a flag on that node, so that any other threads that try to check this again, like it simply will not update it, and it ends. So if there is a change, then we add all the neighbors of this P to some working set. And then we simply execute all of them in parallel. And that's how the new algorithm is parallelizable.
Here, so maybe maybe I missed the point here. So from this property, we'll read again, for an age addition or deletion, if the change propagates to a node, if the change propagates to a node more than once, then the effect of the change must be the same. That sounds very straightforward, and I missed the link of how to use this property to further parallel. I missed this point.
Okay, so let's say that some change happens, right? And then the points2 set of this is updated. So we need to propagate the change.
Yes.
And so when we propagate, we can propagate all of them in parallel. Yeah, then that's it.
So the parallel is that for each thread or for each process, they are processing only one path.
They process only one path. Yeah.
So let me go more detail. So let me use two colors. This is supposed to be path 1, and this is supposed to be path 2. Okay. So if we want to parallel, that means we take each path into a process or thread and propagate the object.
Yep.
And what if there's this link here? Sometimes multiple paths share the same object. So there's supposed to be another path goes through this direction, right?
Yes.
In this case, do we need to synchronize that?
There's I think still need, but it's very minimal because in this
very minimal. How do you make sure it's very minimal?
Right, because there's each node has just a flag whether it's changed or not.
I think this property is just okay. So that means once each node or each variable has been flagged as it's changed, there's no need to further propagate through this node. Am I right?
Yep.
Okay.
Yep. So it will just stop here and then, yep.
Okay.
Okay. So that's the part for the pointer analysis, and then the second part is happens before graph. So honestly, this one, right? All the what they did is simply just to create like a symbolic link for different methods and threads. So they split the graph into subgraphs for each thread and method. And each subgraph have two fields, right? One is the ID of the thread or the method. And then the second part is a trace. So any change in the method statements will only need to be updated once. And the different changes will be done in parallel because each subgraph are independent from each other. Okay, so I'll show you an example of this subgraph. So let's say this is the main thread, and then we see that each of these statements correspond to some nodes inside here. And then when we call a new thread, right? So this new thread will have its own subgraph like this. Yeah.
So just like we organized, so each node is actually a thread. Each subgraph is actually a thread.
Each subgraph, yeah, and it also can be a method.
Okay.
Yeah, so that's basically it.
Okay.
Okay, yeah, so bug detections, and for every conflicting pair of read and write nodes from different threads, yeah, so previously we see that there's a change, right? So let's say this new call M2, then for every change, we will compare it against So we're looking at the variable. So let's say we created this new thread, then there's X here, there's an X here, then we will just compare all of it to see if there is a happens before relationship. And
Happens before, can you give me the examples? And how we add an age or how we add a node on the SVG, and then it will, so there are supposed different rules for race condition and deadlock, right?
So for race condition, they simply detect between two nodes, right? Is there lock protection, and is there happens before relationship? Yeah, actually, so if there's a lock, then there's already a happens before relationship. For the new SVG graph construction, the nodes are still the same from the previous construction, but for the edges, they simply create a new edge. So if there's a method call, then there's a edge from this call statement in the invoking graph to the subgraph. And then for start and join, it's the same thing. So there's now a new edge with the thread ID as the identifier. Yeah.
So basically in the new graph, each node is either is method call abstract, right?
Sorry, call abstract.
In the new SHP graph, it is either each node is either a thread or a method. Right?
Yep. Yep.
And the link between their statement. And now I'm curious about the rules to detect race conditions and a deadlock.
The rules. Okay, so let me try to recall.
Yeah, you can think about it. So you spend a lot of presentations on how to construct a graph and how to conduct incremental analysis on SHP and the pointer analysis, right? But of course, I understand their main contribution might be building the graph to conduct incremental analysis more efficient. In this case, and how to detect the rules supposed to be is not their contribution, right? It's not a contribution of this work, but I'm a little curious about how the rule is designed here.
Yes. I cannot recall it off the top of my head, but for conflict, I wrote it down somewhere. But if I'm not wrong, right, it's for each change, like you see here. Let's say that.
So basically, if we want to detect the race conditions of deadlock, we're just analyzing one graph. We're analyzing two graphs. The graph for pointer analysis graph, so the SHB graph, right? Based on these two graphs, we can really detect whether there's the race condition of deadlock.
Yes.
And
yes. How? So for a change, we can see that there'll be some new nodes added. So I think maybe we take, for example, this graph, right? Let's say that this is the new one, right? So for this new one, we can see that there are conflicting variables, like they are writing to the same variable. So what the algorithm will do is to check between each node whether there is happens before relationship and if there is a lock protection.
So that means that if two variables which does not happen before relation and there's no protection of lock, there is a dead end. So there's a race condition.
Race. Yeah.
And
so for each X, right, there's like sets of objects, right? So there's a lot of objects in their points to set. So for each object, now they have to, they also have to do this check.
Okay. I got it. And how about the deadlock condition?
Yeah, so for deadlock, now there's also a lock dependency graph. So
and the lock dependent graph is coming from which graph? It's for the SHV.
It is both, right? So we'll go through it in the next slide.
Okay.
So yeah, so we use the points to graph to determine like all the objects that has a lock, right? And then each one, And then from the happens before, we see if there's a dependency between the lock. Okay, so yeah, let me go into more details. Okay, so there's a lock dependency graph.
Okay, so they construct the lock dependent graph from the SHP graph and the pointedness graph.
Yeah, so basically there's a cycle if I acquire a lock and then I acquire another lock before unlocking it. So in this case, let's say that I do not have these two lines at first.
So these T1 and T2 are actually happen before relation.
This T1 and T2 are not really.
Right, so happens before the event of locking O1 happens before the event of locking O2.
Yes, for a given thread, yeah. Yes, actually, yes. So there is this, right? So let's say that we add in lock O3.
Okay, the basic idea, not given right, the basic idea is if there is there's a loop for two locking events, then there will be a deadlock.
That's right, yeah.
Let me see, for T1, it is locking 1 before locking 2, and for T2, it is locking 1. Okay, let's see. So okay. Am I right? Maybe you confirm because you are the one who really know the details.
It's correct. That's exactly what the paper says also. So as long as there's a cycle, and then you see that in the cycle there are two different threads involved, then there's a deadlock.
Okay.
Yeah. So that's it for the paper. For the experiments, how they did it is to run the whole analysis on a fresh code base, and then for each statement they delete it, and then you run the incremental analysis, and then we add it back and then run the incremental analysis again. So of course it's a lot faster. So this is taken from the video recording of the paper presentation, and we can see that this is like your orange and blue are the previous algorithms, and then the newer ones are gray and yellow, and like you can barely see them. So it's a lot faster, and here are some benchmarks. Okay, so it's done on 14 real-world Java projects, and they all have a lot of lines of code. Yeah, and generally, the echo, which is their previous work, runs around like it takes.
And
15 minutes.
How do they affect evaluate the effectiveness? Of course, they improve the efficiency. They do have some proof. But is there any evaluation of the effectiveness, or whether they will still keep the original point analysis and SHP graph analysis working? Whether this efficiency improvement idea affected graphics?
Sorry. So are you asking about whether there is any like more false positives or false negative? Yeah. Okay. Yes, so essentially the algorithms give the same outputs. So whatever echo outputs is exactly the same as default. And so apparently there are some false positive, but the rates are the same.
Sorry, what is a false positive?
Yeah, there are some false positives because according to the paper is the inherent false positive of static analysis.
Okay, so both of them makes the same false positive.
Yeah.
Okay.
For the exact number.
And how they label the ground truth?
How do they label the ground truth?
Yeah. So think about it. For now, okay. So if they do the analysis, they do this. So basically, they're given a project. They remove one sentence and add one sentence incrementally, and then form analysis, right? So they do not apply on the real world code evolution.
Yeah.
Because you can see, if we remove one sentence and add one sentence back, the change on the original graph is very small. You get my point? So sometimes if we want to deploy in the real scenarios with one version, so anyway, so if we would want to create some code, this may involve maybe tens or hundreds of code change. And then they have to evaluate their performance on this kind of the code evolution or code difference. Do they?
But
Have they?
But the working context is that the developer, like for every line the developer types, it will send this, it will start this analysis. So
Okay, so
the use case is as such, like one line remove, one line delete, this kind. And there are suggestions for the, like, in case there's a batch, right? I think they just deferred to some software engineering framework. So yeah, I think they just said that if there's a batch, they will simply process it one by one.
okay. Please go on.
So let me think. Right. So for D4, so they also set it up such that they run it on a client machine. So D4 is an instance of the algorithm, but running on, it's a single threaded run. Yeah. And D48 is the one with like 48 threads.
Okay, so its improvement is.
So the improvements are like a few hundred times. So yeah, from echo, right, it's like from a few minutes down to sub-seconds kind of improvement. Yeah.
Okay.
Yeah.
Keep going up.
Let's see. I think that's basically it. And so I have two more questions. If anyone wants to try.
Okay. So you know the answers. You want to add more to try.
Yeah, actually, the second one is kind of already covered. So there's just one. Yeah, it's a bit open-ended. So I don't know. Maybe Darian.
I have to confess that I still don't quite understand the SHB.
Yeah. Okay. Sure. I feel that the paper was also not super clear on exactly how it will work, right, for different objects. So let me just show you. Right. So have you seen this kind of representation of like execution? So like each node is some event, right? And then you have this kind of relationships.
Okay, yeah, I've seen this before. Yeah.
So this is basically their static happens before graph, but in another form. So each line, right, is a thread, but in this case they grouped it in the box, and then so yeah, so for each edge is the edge spanning the different threads like that.
Okay.
Okay, so from such representation, let's say that there are repeating sequences, right? There's some repeating sequences of calls if they are in a same method, for example, right?
Yeah.
So the improvement is simply to just store a reference to a single ground truth of such a sequence. So instead of all these sequences, they just show like now it's just one whole node, and then now it points to here. Does that make sense?
Okay.
Yeah. So that's it.
But basically, if they point to the two nodes, whether it will introduce a false negative. So consider this: if the thread T1 just a thread T1, T2, right? And suppose there's a potential that the race conditions happens. Well, here it is going to write some x, and here, and this node is still going to write an x. And how do they detect this potential write x event for race condition?
So they will just see that
The most, at least for me, the most safest way is that to inline the code of the method call back to the thresh. Suppose the node here is the call method n, right? And this is the code of n. So the best way, the first and most naive way is just to inline all the execution, all the events back to the call, and then we define the happens before relations. Because anyway, if there's a method call, there is supposed to all the instruction, all the events inside the method call will not have the happens before relations with each other, right? What I mean is that if we inline the code here, and if we inline the code here, at least we can build the happens before relations on the trace instead of having some indirect correlation.
Yeah, I get what you mean. They actually glossed over their data race detection part because I think they said that it was covered.
There must be some details. So I think your question, because all the discussions is only you and I are interacting with each other. So definitely, I think Darius is kind of lost in the middle. So then the next I decide to rephrase the whole presentation of Yuchen. Maybe based on my understanding, it's easier for all of you to fully grasp what it is. But anyway, you spend the time to attend a talk, you need to have some takeaway. Maybe you can give me 1 or 2 minutes to finalize the presentations. Then I might reorganize the story from my version. Okay, Yuchen, please.
Okay, so maybe I'll just give a general overview of how the whole thing works again. So
okay, so you have already finished all the presentation, right?
Yeah.
Okay.
Yeah. So the main thing to look at is this part, right? This part of the graph, and basically what happens is that now for every change that the user makes,
I think this part is very clear. I think that Darren definitely understands this part. So the change. So I think one of the, if I'm the one giving the presentation, there must be a background. And if we do not analyzing, if we do not go through the background, it's very hard to understand why we need the incremental pointer analysis and why we need the incremental before analysis. So maybe I have a try. I think if you want to, Yuchen, do you have anything you want to add to overview? If you just want to explain this graph, I think you typically clarify this graph. This is not the part that confuses audience.
Okay, let me think.
So maybe I will have try, or you want to have try yourself. At least we let Darren to fully grasp the point.
Yeah, okay.
Okay, we'll go back to the previous slide. And yeah, this graph. So here, this graph. So let me start with rationale and motivation. But I still keep reorganizing Yuchen's point. So if I'm wrong, Yuchen can pinpoint. So here, you have 3 issues. The first issue is called the data race problems. And the second issue is called the deadlock problems. Darren, do you still have any questions on what is data race and what is deadlock? So you have to understand these 2 problems, or two problems well, so that you can understand why we need pointer analysis and why we need to the topic before analysis. Otherwise, you will feel quite confused with all the following process.
I think I'm okay with data race and deadlock.
Okay. Okay, so now think the next move on. So in order to analyzing the data race problems, we usually need some rule, right? Those rule is supposed to be fairly straightforward. Suppose here we have two threads, right? T1, T2. Given it is a concurrent program, there's no guarantee whether T1 and T2 will execute first, right? So in this case, if there's an event that's called X written event, and here is also X written event. If there's X written event in T1 and another X written event in T2, and T1 there's no guarantee T1 let's say this E1 and this E2. If there's no guarantee E1 can always happen before E2, or vice versa, that means the guarantee E2 can always happen before E1, then the program outcome becomes non-deterministic. So you get this point, right?
Yeah.
So in this case, we will report the data race problem because we do not know. Because if we run a programs, the outcome is supposed to be deterministic, and the concurrency, the feature of concurrency, is just to improve the program efficiency instead of causing down randomness, right? So this is a basic assumption. So in this case, E1 and E2, if there's no guarantee to make sure E1 happens before E2 or E2 happens before E1, then there's a data race problem we report it. And similarly for deadlock, if there's a, so if we know that the event of locking happens before, so here's the case. So when there's two lock conditions, it means that the T1 and T2 have to synchronize on these two events. Let me see, E1 and E1 2. Here is E2 and E2 So if we want the program to execute well, so we have to make sure. So here the happens relations.
No, I mean, so the issue here is the same as the previous one, that we don't know whether the E11 will execute before E21, right?
Yes. Yeah, that is you're right. So here, let me see how. Yuchen, can you draw the loop condition for on this graph? So here,
The loop condition.
yes, the loop conditions. So the execution of lock is just depends on. Yeah. So anyway, so I think Darren pinpointed the good argument that there's no guarantee that E11 will happens before E21 or vice versa. But the more important problem is that if we want to execute, if we want to enter the if we want to execute it, if we want to enter the critical condition ordered by E12, it depends on whether E21 has been executed, right? Similarly, if we want to verify the E11 can be executed, it depends on whether E21 has been executed, right? So there's actually no guarantee about happens before relations. So here so anyway, I'm not sure whether I have explained the dialog clearly, but anyway, the point is that if we want to know the data race problem and the dialog problems, we have to know the event, like read variable and that happens before relation between the read event and write event. Is that true? Right? So if we want to do these, the basic idea is that for each event of the thread, we need to build the happens before relationship. So that is why we need to use the happens before relationship graph. So that's why we build these ones. And next thing is we want to discuss is that why we need to the point two analysis. you can think about it, why we need the point to analysis. So the point is here, suppose in C++, for Java maybe, before Java there's still a Java object issue. So this X, and suppose there's this variable is a Y, okay? Maybe this X and this Y point to the same memory location. Point to the same memory location. In this case, we also need to guarantee E1 and E2 have a happens before relationship. Right? So this is for the completeness of the program analysis. Okay. So by this means, first we build a happens before relationship, and then we're going to enhance the happens before relationship with a point analysis to know which variables are actually the alias analysis, so that we can define rules to detect data race problems and the deadlock problems. Okay. I made myself clear or understood.
Yeah, I think so. Yeah. Okay.
Okay, so that is the rationale why we need a happens before relationship and a point to analysis. And after that, we go back to what in turn as described. Remember, please go back to the next slide. So each time we make a modification, you can think about it. So the most brute-force or naive way is that each time we make a minor modification and the whole program change, right? We can connect the whole program point to analysis and the whole static happens before analysis and get really good report result. Of course, it is very expensive. So the idea is that when we have make a minor change of the delta of a delta statement, we're going to how can we incrementally update the point to analysis graph and the HB graph so that it can still report the potential data race and the deadlock problems in a very in a few seconds or milliseconds and return back to the user. So that's the basic idea. So here the challenge comes like, suppose we have a minor modifications on the original code, how to incrementally update the point analysis graph and the HB graph. Once we got these two graphs, then we apply the rules to detect the data race and deadlock problems and send it back to the user. So that is overall picture. But I think Yuchen makes this picture very clear and understandable. But if I'm Yuchen who will give me the presentations, I will first tell the rules to apply to combine point analysis and that happens before relationship, graph, and then we'll go through all the rest. Then that will be very clear. Okay, Michelle, please, Darren, do you have any question here, or shall we?
None for now.
Okay, so Michelle, please go back to the last one. Yeah, so now here, this is questions. So where would you SHB graph
Yeah, okay.
underperform? Okay.
So
here, so you still need to compare the new graph presentations and the original graph presentation, right?
yeah, so as we said, right, what's the original? Okay, but anyway, as we said, right, so the main improvement from the previous one was just that we collapsed some of the repeating nodes into a new subgraph, right? So, but somehow this difference underperforms in certain scenarios.
I didn't get that. So what's the difference of the new presentation?
Right, so the new presentation basically saves on some memory space, right? Because now all these inline representation, right? Now we just like, it's compacted into one single subgraph. So Okay, maybe I just say the answer. It's actually not that it's not that complicated. So basically, when there are very small lines of codes, when the code base is very small, then the cost of maintaining and upkeeping all the different subgraphs it becomes more expensive than to just store it in the inline fashion. So that's basically the answer. So when there are maybe your lines of code is less than 50, that's the threshold that they gave. You see that now the incremental updates to SHB is now slower.
You mean the new SHB or
Yeah.
the old SHB?
The new hit SHB. Yeah.
Okay. So the point is that if the method contains a lot of statements, then if the older version, that inlining all the method code becomes more expensive.
Sorry, which one is more expensive?
I mean the inlining. So that means the inlining the method instructions back or the method events back to the core site is more expensive.
This is actually less expensive.
Less expensive. So the wait. So the new presentations is the inlining version.
So this works because for large code bases, you only need to update one point, right? But now you have a lot of subgraphs. So the advantage for the old one is that if your program is very simple, then there's less things to keep track of.
My question is that the older version inline the method call. Right now.
Yeah.
Okay. So simple one definitely that is the answer. Okay.
Yeah, because the older one is simpler. Yeah, that's it. Okay.
Okay, but when the method becomes more complicated, the inlining becomes more complicated and extensive.
Yeah.
Okay, the Darren and the question is that maintaining reference can be more expensive than savings if each reference is to a small input. Yes, I think the answer to Darren's question is yes.
Yeah, correct.
Okay, and how does parallel dialectic work? Yes, Daniel. Okay,
Yeah,
so
actually,
I think we have thoroughly discussed this question.
Yeah, we have already discussed. So like figure 6 case 2 is in this case, right? So when I check the reference for the incoming neighbors for W, yeah, so we see that even if I see that there's no change at first, the change will eventually propagate and I will eventually get it correct.
But I still have a question on here. So my point is that can you go back to the previous slide 17. So the point here, suppose there's another variable x, right? So how this can be parallelized? Suppose x is have O2, right? But here in the original version, suppose this O1, and O2, right? So and the R here is has O2, okay? And here's O1. So if we find if the deletion happens between this one and this one, okay? If we only consider individual paths, giving the W, we will first remove O1 and then remove O2, right? But how they can remove in parallel? We still need to merge the result. If we look into this path, we should remove O2. And if we look into this path, we should remove O1. So if we parallel the computation, the one parallel result will be W01 and the other will be O2. And this is complex, right? These two results will conflict. And will they merge their parallel computation results?
So according to the algorithm, it will do one thing first. But if you ask me, right, I feel like for each change, maybe you can maintain a separate flag for that change.
I think the answer for you is that, so it will only take the path origins from the same change, just like your slide 19. Let me go back to the slide 19. Yeah. So and even if it's for single pass, if all the change, all the propagation, if the propagations all the propagations will have the same effect, you can just simply remove the rest and keep only one path. Right.
Remove the rest.
For example, there are two paths, and we can just throw away one path. If we want to update the point2 set of Q, we can just remove one pass, and we just remove the rest and only keeps one pass of Q.
Actually, we can't tell what, because the propagated change from both sides may be different.
If it is different, how do they merge? The result is that the effect of the change must be the same.
Yeah, so in this case, right, if your change does not update the object, then we actually cannot tell whether this change is like final or not. It's only after this, like that actually removes an object, then we can tell that that's the final operation. Then the effect is the same.
But if the effect of the change must be the same, then delta 1 is supposed to be equal to delta 2. Am I right? Because we know P, there is an object missing from P. For example, for P, the delta of the P is to remove O, right? And the P will have multiple pockets reaching Q. So the delta propagated from P should be the same. Is there something incorrect based on this difference?
I'm a bit lost. Can you repeat the?
The point is that P will have two passes reaching Q, okay? And for the delta, the delta quantity set is to remove Q, remove O. So in this case, such a change will propagate through the graph. And for the delta from the delta 1 from the first pass will be the same as the delta from on the second pass.
If I have the object O and then it reaches both like this, then the change here will be empty, right?
Yes. Okay. So you're right. If there's O, still be FR2 is still pointing to O, it will be empty. But then in the properties, correct? We still need to look into the property result of multiple passes. And they're supposed to be a merge result, right? And it takes the unions of the. Right. So here, the point here, R1 will not be pointed to O, but P and R2 will point to O. And now the relation here, the case is that now the edge between PR1 and the PR2 are removed, or the P itself has been removed. In this case, we are trying to propagate the delta from P to Q, right? Because the object pointed by the object of P, the object P has disappeared. So in this case, such a dimension needs to be propagated. But if we propagate it from the first pass, we will have a conclusion. We will have a conclusion that we need to remove rules, right? But if we propagate it from the second epochs, what is the result? The result is that we should not remove all, right?
Yes.
So the point of being parallel is that they will not interfere with each other. So if we have the parallel relation results, so if each process or each thread were responding to propagating one path, then when both paths reach Q, we do union the result or merge the result of each individual path. Then in giving your example, the effect of change must be the same. Is that correct? Or we have different understanding or interpretation on this sentence?
I think it's not really the merging, right? Because according to your change, if there are two removed edges, then these are actually two changes. These are two addition or deletions. So technically, we are talking about different.
They understand. They understand. If we not remove these two edges, means that we remove the P.
Okay. If we remove P, is it merging? I'm not sure if merging would be the right word, but
anyway, the result turns out to be that P1 and P2 have some inconsistency. We have to have a way to make them consistent.
yeah. I can't remember like the exact construction, right? But I like thought about it before. So
Okay, so here I think maybe we should since it's 5 p.m. I think we should call a day for today's presentation. But anyway, both Ruofan and Yuchen make perfect presentations. But I have a comment for Yuchen's storyline. So giving the presentations, your presentations is assume the audience have well understand the what is the point to and have well understand how the deadlock and the race condition be addressed based on the point to analysis and the SHB graph analysis, right? And based on these assumptions, some audience like Darren's kind of lost. But anyway, your presentation is fairly clear, and I fully understand you master a lot of details here. But when you are making the presentations, since Ruofan will actually send me messages to say that whether it's appropriate to introduce the variational autoencoder again. I say it is. So maybe when you are making the presentations, you need to have a expectation of the knowledge of your audience. Since our audience will, because our group has have some hybrid topics or have some distinct topics. So if you want to have more collaborations or have more discussions, it's better to equip the audience with more knowledge. That is better. So in this case, you will find that despite we're talking about the state of the art research work, but we don't mind to keep introducing some basic concepts like autoencoder, and also for here and for program this part, it's better for people to understand what is control graph, what is data graph, and what is point analysis, what is the happens before graph here. So with all those concepts here, and people can follow. But anyway, you make a very good presentation today.
Okay, I agree. I think I'm missing a bit of the narrative of the whole thing. So I'll add it in for the next presentation.
So your presentation is much improved on your previous version of presentation. Okay, so maybe you can call it a day. And for the second paper, I think what we need to understand is that how do we write a system paper or a peer paper? So the second paper is published in some top tier conference like peer DI. So basically to look into more details and have the theorems and proofs. So this kind of research requires more detailed algorithm improvement. And here I assume that in the paper there's nice and theorem definitions and dilemmas, but also have some algorithm analysis like worst case analysis here. So that's all. You can feel that for the first paper, it's more AI oriented. It's an application of AI. And for the second work, it's more has more flavor of computer science. So we have the worst case analysis. We have the graph analysis. We have more detailed algorithms. And this actually the different flavor and styles. It's good for us to know both. Okay. So thanks again for everyone to attend the presentation. Let's put it. Okay. Bye.